Before artificial intelligence, before servers, before data centers the size of cities, there was sand. Not metaphorical sand, real sand. Grains scattered across beaches and deserts, shaped by wind and water over millions of years. Inside those grains lies silicon dioxide, the material that quietly forms the foundation of nearly every digital memory system on Earth. Today, we're going to follow that material step by step, from sand to purified silicon to the microscopic structures inside RAM, and finally to the data centers that power modern AI. Most sand is made primarily of quartz. Quartz is crystalline silicon dioxide, one silicon atom bonded to two oxygen atoms. But the sand you see on a beach is not pure. It contains iron particles, organic debris, clay, and other minerals. To use it for electronics, the first step is purification. The sand is washed repeatedly to remove dirt and organic matter. Magnetic separation removes iron impurities. Chemical treatments strip away unwanted metallic contaminants. After these stages, what remains is high-purity quartz, nearly pure silicon dioxide. But silicon dioxide itself is not usable for electronics in that form. The silicon atoms are chemically bonded to oxygen. To extract pure silicon, the quartz is placed inside a submerged arc furnace along with carbon, typically derived from coal or coke. The temperature rises to nearly 2,000 degrees Celsius. At that heat, carbon reacts with oxygen, forming carbon monoxide gas and leaving behind elemental silicon. This process produces metallurgical-grade silicon, about 98 to 99% pure. That sounds impressive, but for microelectronics it is nowhere near sufficient. Memory chips require extreme purity, often 99.9999999% pure silicon. To achieve this, the silicon undergoes chemical refinement. It reacts with hydrogen chloride to form a gas called trichlorosilane. This gas can be purified through repeated distillation, removing trace impurities. Then, through the Siemens process, the purified gas decomposes at high temperatures and deposits ultra-pure silicon onto heated rods. At this stage, impurities are measured in atoms per billion. Because inside a memory chip, even a single misplaced atom can disrupt electrical behavior. Now the purified silicon must be structured. Electronics require silicon arranged in a perfect continuous crystal lattice. Using the Czochralski process, ultra-pure silicon is melted inside a crucible. A tiny seed crystal is dipped into the molten silicon and slowly pulled upward while rotating. Over many hours, a large cylindrical crystal forms, with every atom aligned in a repeating, orderly structure. This crystal, sometimes over a meter long, becomes the foundation of memory chips. It is then sliced into thin wafers, less than a millimeter thick. These wafers are polished to near atomic smoothness and cleaned in ultra-clean environments where even microscopic dust particles are unacceptable. Now we begin building RAM. Most server memory today is DRAM, Dynamic Random Access Memory. Each DRAM cell is deceptively simple, one transistor and one capacitor. That's all. But billions of these cells are packed into a single chip. The transistor acts as a switch. The capacitor stores electric charge. A charged capacitor represents a 1. An uncharged capacitor represents a 0. Silicon dioxide plays a critical role inside both components. In the transistor, a thin layer of silicon dioxide sits between the gate and the silicon channel. This layer, only a few nanometers thick, acts as an insulator. When voltage is applied to the gate, an electric field passes through the silicon dioxide and controls current flow in the channel below, without physical contact. This precise insulation makes switching possible. Without silicon dioxide, the transistor would short circuit. There would be no controlled switching, no logic, no memory. In the capacitor, silicon dioxide, or advanced materials derived from it, acts as a dielectric. The dielectric prevents stored charge from dissipating too quickly. However, in DRAM, charge always leaks slowly. That's why memory must constantly refresh itself, often thousands of times per second. Each refresh restores charge before it fades. This constant refreshing is why it's called dynamic memory. It is not static. It is in continuous electrical motion. Building these structures requires one of the most precise manufacturing processes ever developed: photolithography. A light-sensitive material called photoresist is carefully spun onto the silicon wafer, forming an ultra-thin, uniform coating. The wafer is then exposed to intense ultraviolet light through a patterned mask that contains the blueprint of microscopic circuits. Wherever the light strikes, the chemical structure of the photoresist changes. The exposed regions are developed and washed away, revealing portions of silicon beneath. Chemical etching then removes material in those exposed areas, carving patterns that are measured in nanometers. This process is repeated again and again, each time adding or removing material with astonishing precision. Doping follows, where controlled amounts of elements such as phosphorus or boron are implanted into specific regions of the silicon lattice. These atoms alter how electrons move through the material, creating conductive pathways or insulating barriers exactly where needed. At this scale, engineers are not shaping metal, they are shaping electron behavior. Layer after layer is added: crystalline silicon for channels, silicon dioxide for insulation, high-K dielectric materials for capacitors, and multiple metal interconnect layers to carry signals. Between each conductive layer, insulating oxides prevent unwanted current leakage. Alignment between layers must be accurate to within a few nanometers. Even a slight deviation can render a chip unusable. A modern DRAM chip may contain dozens of stacked layers, forming a compact three-dimensional architecture. Billions of transistors and capacitors are arranged in repeating grids, connected through a maze of microscopic copper wiring. The result is not a flat circuit, but a dense electrical city built vertically and horizontally at atomic scale. Silicon conducts. Silicon dioxide insulates. Conductors and insulators alternate in carefully engineered balance. Together, they create controlled electrical pathways so precise that electrons flow exactly where they are intended, and nowhere else. Once fabrication is complete, the wafer enters a testing phase. Automated probe systems touch microscopic contact pads and verify functionality for each individual die. Not every chip survives. Imperfections at nanometer scale are unavoidable, and defective dies are mapped and discarded. The functional chips are then separated from the wafer in a process called dicing. Each tiny die is mounted onto a substrate and connected using microscopic bonding wires or advanced flip-chip solder bumps. Protective encapsulation shields the fragile silicon from physical damage and environmental contamination. Heat spreaders are added to manage thermal load because even memory generates heat when switching billions of times per second. The finished memory chips are mounted onto printed circuit boards, along with supporting components such as voltage regulators and configuration controllers. This assembly becomes the RAM module, the memory stick inserted into a server motherboard. Each module contains multiple DRAM chips. Each chip contains billions of memory cells. Each memory cell depends on silicon dioxide for insulation, field control, and charge retention. The entire structure, from transistor gate oxide to capacitor dielectric, traces back to refined sand. What began as loose grains on a shoreline is now organized digital memory capable of storing and retrieving information at incredible speed. Now scale this up to a data center. Processors calculate, but memory feeds them. CPUs and GPUs execute instructions at extraordinary speed, yet they constantly wait for data to arrive from RAM. The faster the processor becomes, the more critical memory bandwidth and latency become. Without sufficient RAM capacity, even the most advanced processors are forced to idle. RAM determines how many virtual machines can run simultaneously. It determines how many users can connect at once. It determines how large machine learning models can grow and how much contextual information an AI system can hold during inference. In large-scale AI infrastructure, including systems developed by OpenAI, memory is not just a supporting component. It is one of the primary constraints on scale. Training large models requires enormous memory pools to store parameters, gradients, and intermediate computations. Inference requires fast access memory to maintain conversational context and process incoming prompts in real time. More memory enables larger models. Larger models require more parameters. More parameters require more RAM. The demand compounds. Memory becomes the bottleneck. Data centers are often described as warehouses of compute power, but in reality, they are equally warehouses of memory. Vast installations filled with silicon modules constantly refreshing, storing, and delivering data at nanosecond speeds. Without RAM, processors have nothing to process. Trace it backward one final time. Sand becomes quartz. Quartz becomes silicon dioxide. Silicon dioxide is reduced to elemental silicon. Silicon is purified to near perfection. It is crystallized, sliced into wafers, polished, patterned, layered, etched, insulated, doped, and connected. Transistors switch. Capacitors hold charge. Chips are packaged. Modules are assembled. Servers are installed. Data centers hum with synchronized electrical motion. Artificial intelligence runs. The cloud is not abstract. It is engineered matter organized with atomic precision. Beneath every advanced digital system lies a material once scattered across beaches, shaped by wind and tide long before humans understood electricity. That's all for today. Don't forget to subscribe for more interesting topics.